So my plan for today is as follows. I'm going to introduce the Bruhat-Tits building of type A tilde D, and I want to also introduce their fundamental apartments. Then I want to talk about random walks on cells of a subspecial complex and the cutoff phenomenon. Then I will define what a Ramanujan graph is, and I will wave my hand about what a Ramanujan complex is. Then I will review the proof of cutoff of walks, simple random walks on Ramanujan graphs by Lubetzky and Peres. And I will introduce a viewpoint that will be helpful for me afterwards using the folded department of the one-dimensional building. And at the end, I will try and explain what innovations Ori and I introduced to this world that enabled us to prove a similar thing about Ramanujan complexes. So as I wrote here but didn't say out loud, this whole talk is based on the work I've done with Ori Parzanchevski. Okay. So let's start with, so I made for myself a goal to explain in the most succinct way and in a way that you will actually understand at least what is the combinatorial structure of the building. And then I will just wave my hands about a group that acts on this building in a nice way, but we will start with this. So what is an integral lattice? So an integral lattice is just a subset of z to the d of the form a matrix, an integral matrix times z to the d, such that this integral matrix is invertible over Q. So here are 3 examples. They are not examples of integral lattices, but just lattices. And I'll just try and use the board for a moment. So it will take me a moment. Great, so let's check with the participants that everybody sees my board. So touch yes if you see my board and everything seems okay. Great, thank you all. Okay, so the first example is z to the d itself. Okay, which is, for example, 1, 0, 0, 1, z to the d. Okay, and this is thinking of these 2 vectors as generators. We can also look at, for example, 1, 2, 0, 1, z to the d, which is the same as taking the generators. So let's try another color. So I'll do this in orange. So one of the generators is the same, the 1, 0 generator, but the second generator is 2, 1, right? So it's this thing. And I claim that both matrices generate the same lattice. So it's not a unique representation of the lattice. There are many ways to represent the same lattice, and we will talk about different ways to represent the same lattice. The second one that I showed here is not an integral lattice, but it's an interesting one. So let's talk about it a bit. So if this is 1, 0, this one, these are 60 degrees or pi over 3 radians. So this should be cosinus pi over 3 sine pi over 3. And this matrix is invertible, right? The 1, 0 cosine pi over 3 sine pi over 3. And actually it generates a lattice, which is a tessellation of the plane using triangles. It's the vertex points of the tessellation of the plane using triangles. And here is another lattice that can be generated, for example, by this and this vector. Okay, so only one of them was integral. Only the first example was integral because I claim that I'm only interested in such lattices that are contained in this left example. Great. So let's go back to the slides. Okay. So first of all, as I said, using my voice, any lattice, any integral lattice is contained in the z to the d, in the lattice that I showed before. I only gave examples in the 2 dimensions, but you can clearly understand what is the general case. And I claim that a matrix defines the z to the d if and only if it's invertible as an integral matrix. So it's invertible, and its inverse is also has only entries that are integral. So only integers in the entries of its inverse. Okay, so from that, it's easy to see that the lattice AZ to the D is the same as BZ to the D if the inverse of one of them times the second is in the invertible matrices, the integral invertible matrices. Okay. If there are any questions, please, you can either raise your hands or ask out loud. So I'll just keep on until someone will stop me. Okay, great. So what is the covolume of a lattice? It's just the determinant of one of its representatives in absolute value. And I want to define another definition. So 2 lattices are homothetic if one is the an integral so it's the correct thing to say here is Z homothetic, and it's if there exists an integral number, an integer, such that one lattice is the multiplication by this integer of the other lattice. So either L is alpha L prime or L prime is alpha L. And we denote 2 homothetic, Z homothetic lattices by this approximate sign. And we call a lattice primitive if there is no integer such that L over this, except, okay, so I should have written here except 1 and minus 1, right? But for all non-trivial integers, L over alpha is not an integral lattice by itself. So if I look at homothetic classes of lattices, it has a representative which is primitive, okay? Like the smallest representative in this homothetic class. Great. Okay, so now I can explain you what are the vertices of the building. So, okay, the headline of the first interesting slide was the Bruhat-Tits building. So we're actually going to construct some combinatorial thing. And this combinatorial thing is also a geometric thing, which is the building, which is specifically a simplicial complex. So our goal is to construct a simplicial complex. First, we will construct its vertices, then we will construct its edges, and then we will say something that will construct all other cells of the simplicial complex. Great. So from now on, let's fix a prime number P. Maybe I will change it throughout the talk, but P is a prime number. And now I will define the vertices. So this 0 sign over the XPD means that we define the vertices, and the XPD notation means the Bruhat-Tits building, actually of dimension D minus 1. So this D is 1 more than the dimension of the actual simplicial complex. And the P downstairs is the prime that we constructed this simplicial complex with. Great. So what are the vertices of the building? Okay, so there are many ways to define the vertices of the building, and you will see that actually this is not such a good way to define the vertices of the building, but it will be very helpful if you don't know what buildings are before, because this is a very understandable definition of what the building is. So you can take the integral lattice that have a p power as a covolume. So the covolume of these lattices should be a p power. And we think of 2 such lattices as the same if they are Z homothetic to one another. Okay, so as I said before, for any homotopy class, we can choose the smallest. It's actually the smallest. Okay, so I don't need even to do like parentheses. So we can just choose the smallest representative inside this set. And then we think of the points as primitive integral lattice with a p-power covolume. Okay, so this is just choosing the smallest representative of every set from the first definition. And I claim that actually for every such primitive integral lattice with a p-power covolume, you can take a matrix that represents it of the following form. Okay, so on the diagonal, there are p-powers. This will ensure that the determinant of this matrix is a p-power, so the covolume will be a p-power. This is good. This is a good sanity check for us, right? So the diagonal is p-powers, and under the diagonal, the main diagonal, there are only zeros. So this is an upper triangular matrix. And above the diagonal, there are integer numbers with the following conditions. So first of all, these numbers, so in the first row, there are only integers between 0 and p to the n1. So they should be strictly smaller than p to the n1. And in the second row, there are integers that are strictly smaller than p to the n2 and larger or equal to 0. So non-negative integers that are smaller than p to the n2. And so on. So every row is conditioned by the p-power on the left side of the row. And my last condition is that the GCD of all the numbers in the matrix should be 1. So this will ensure us that this is actually a primitive lattice. If this was not true, the last condition was not true, this wasn't the primitive representative of the homotopy class. Okay, so I just said p-powers on the diagonal, but actually I want all the powers to be non-negative. So there are ways to look at the buildings, not with integers in the matrices, but with other number systems. And this condition comes because you can think of it in other number systems, and it's redundant in our case. Okay, so these are the vertices of the building. Any questions about the vertices of the building? No, everything is clear. Great, let's move along. So now we want to create a graph. So we started with vertices, and now we want to create a graph. So we want to say when are two vertices adjacent to one another. So you take two vertices of the building, and I claim that they are adjacent to one another, and I'll take here the primitive representatives. So when I write L and L prime are in this set, I mean not any representative of the homotopy class, but the primitive one. And I claim that they are adjacent if one of the following conditions hold. Either L prime is a sublattice of L, so as a set of points is a subset of L. And if you multiply L by P, so it's a different representative of the homotopy class, but it's okay. We just multiply by this prime number P, and we get another lattice. And if this lattice sits inside L prime, we say that L and L prime are adjacent, or the other way around. So it can be that L sits inside L prime, but P times L prime sits inside L. Great, so this defines our adjacency rule between vertices. So now we have the one skeleton of our simplicial complex. Let's see an example. So you see here 3, 1, 0, 1. I claim that in the one-dimensional, so x, 2, 3, in the one-dimensional building, so these two, P is 3, these two lattices are adjacent. So first of all, the GCD of all the numbers here are 1 because 1 appears in the matrix. Second of all, you can see that the determinant of both matrices is a power over 3. So the left one has determinant 3, the right one has determinant 9. So these are these matrices satisfy the condition from the previous slide. So let's go to it for a moment. Okay, so it satisfies this condition. And why are they adjacent? So it's quite clear that the right one is a sublattice of the left one. Why is that so? One of their generators is the same. The 1-1 generator appears in both lattices. So I look at the columns and I think of the columns as the generators of the lattice. And 9-0 is 3 times 3-0. Right? So actually the right lattice is contained in the left lattice. Why is P times the left lattice contained in the right lattice? So this is as easy as the first one, right? When you multiply the left lattice by 3, you get 9-0, 3-3. 9-0 appears in both generator sets. And 3-3 is just 3 times the generator 1-1. So by the definition that I gave a moment ago, it's clear that these two lattices, these two matrices are adjacent in the building. Okay, so now we can define the building itself. XPD is the Klee complex of the graph that we got. Great, so Klee complex just means if you see a triangle in the graph, you put a 2 cell there. If you see a tetrahedron in the graph, you put a 4 cell there. If you see a 5 simplex, a 4 simplex, you put a 4 simplex there, and so on and so on. So you just fill up the simplicial complex. Any questions now? No.
Yes, I have a question.
Great.
So by the example that you're doing, in order to check, so if you use the matrix representation that you showed before, in order to check that one is containing the other, is it equivalent to say that each column of one is an integral multiple of the column of the other? Is that how it works?
No, we will see in a moment. No, sometimes you will get linear combinations. So it will not always be. I will show it in a moment. So I will just give you the most general algebraic definition of how to connect to matrices of this form. Great.
Thanks.
So you're welcome. Any more questions? No. Okay. So as before, I have here 2 examples, and I want to draw things on the examples. So I'll go back to my iPad. Just a moment. Technology is amazing. Okay, so I put here these 2 sets. Okay, so on the left side, this is a 1-dimensional building. And actually it's the 3 regular tree. And we'll see what are the vertices and edges in this case. So I'll just write here. I'll name the vertices such that they are actually adjacent in the rule that I gave before. And then I will talk about the example on the right, which is a bit more interesting. It's the 2-dimensional building. Both of the prime here is 2. Okay, I'll write it with black as well. Just a moment. So the prime here is 2. And we will see in a moment that the prime here is 2 as well, because these are the smallest examples. I showed you them. And okay, so let's say that this is the identity matrix here. So it has 3 neighbors. One of them is 2, 0, 0, 1. One of them is 1, 0, 0, 2. And the third neighbor is 2, 1, 0, 1. So you should check that none of these lattices are the same. all of them are contained in 1001. It's quite clear that twice 1001 is contained in both of them, in all three of them. And that's it. So let's check what are the neighbors of 2001, for example. So clearly you can go back. You can multiply, you can have here 4001. This is a neighbor. And also, maybe it's not so clear, but I will tell you what the next one will be. 4201 is a neighbor of 2001. Okay. And again, this is quite clear because 40, when you multiply 2001 by 2, 40 lives inside this lattice. And you can check that twice the right-hand side, twice 2, 1, minus 40 is 0, 2. So 0, 2 also lives inside this vertex, this 4201. Okay, so who are the neighbors of 2101? One of them, just a moment, I'll calculate. Okay, so the way I calculate, I'll just tell you the calculation. You take the vertex itself, okay? So I took the vertex itself and I multiplied it. Oh, no, I don't want the caption. And I multiplied it from the right by one of the neighbors of the identity. So I'll multiply from the right either by this matrix, or this matrix. One of them will take me backwards. One of them will take me back to the origin. And the other two will take me one step further. So let's try them all. So if you multiply 2101 by 2001 from the right, 2101 times 2101, and 2101 times 1002. Okay, so let's just do all these calculations and see what we get. So here we will get 40 and 11, right? So one of the neighbors will be 4101. And it didn't appear yet, okay? The other one will be, okay, that's a bit harder, right? So this is a 4, this is a 0, this is clear. Here we'll get 3, and here we'll get 1. So one of them will be 4301. This will be the second vertex, and we can just guess now what will be the last vertex. Okay, we will get here 2202, but it is easily checked that this lattice is the same as 1001. So it's homothetic to 1001. It's a multiple of 2 of 1101, right? And 1101, you can just add and subtract columns one from the other, and you'll get back 1001. Great, and we can just guess what the next thing will be. So one of the vertices here will be 2102. This will be one of the vertices here. And actually, I'm not sure what will be the other. Probably, I know what it will be. It will be 1004. This will be the other vertex here. Any questions about the calculations I've just done? So I gave you even a formula of how to create new vertices, the adjacent vertices to the vertex that you are at the beginning. So you just check what are the adjacent vertices of the identity, and you multiply them from the right to the vertex that you are in right now. No, great. So let's talk about the second picture here. Okay, so I'll get close to it. Here we have a two-dimensional building, so it will be a 3x3 matrix. So this again will be the identity. And there are two colors of vertices. So the green vertices will be determinant P, and the red vertices will be determinant P squared. Okay, so let's try and write all of them. Maybe I will do some mistakes, but hopefully people will correct me. So the single vertex here will be P1, will be this matrix. This single vertex will be 1, 1P. Oh, I'm already lying. This will be 1PP. And P11, what is the correct way to write it? Okay, so I'll think of it as for a moment. Here, there should be, okay, so this is determinant P. So here, there should be should be 1P1 with 0 and 1P1 with a 1. So this is, okay, so my P is 2, right? So let's write 2. So this is determinant 2, and this is determinant 4. And here I have 1, 0, 0, 2, 1, 1. Here I have 1, 0, 0, 2, 0, 0. Okay, okay, this is good. Here I'll have 2, 1, 1. And I will have the options of a 1 here, a 0 or a 1 here, and a 0 or a 1 here. Okay, so these will be the options for the green. So we have four vertices here. So all of them will look like 2, and then either 1 or 0, and either 1 or 0, and the rest of the diagonal will be 1. This is good. And I think that, okay, so here I'll just have 1, 1, 2. This is what I'll have here. And the red ones are the complements, and I will not write them down, but these are determinant 4 matrices. Things like of the form 1, 2, 2. So things like 1, 2, 2 will appear here, for example, and I don't know, 2, 1, 2 with some inputs. So something here will appear here, and something like 2, 2, 1, and things will appear here. Okay, so this was just, I hope it wasn't confusing. So just ask me questions. This is the time. Like, what happened here? Something that confuses you. Everything is clear. Right, so you can just check and see what's neighboring what here. Actually, now when I look at it, it is clear that these two vertices, okay, that these two vertices are neighbors, right? And both of them are neighbors of the identity, because clearly the upper one is contained in the lower one, and again, clearly twice the lower one is contained in the upper one. So these are adjacent to one another, so I wrote the correct matrices here. So this is a good sanity check. Cool, let's go back to my slides, because I'm wasting lots of time about this thing. Okay, so we saw that. And now I'll give you someone asked before, Francesco. I hope I correctly pronounce your name. Thanks. So he asked, like, what is the rule maybe, or checking that you understand why something is an adjacent vertex to something else. So I'll give you just a formula. Two vertices are adjacent if you take one of these kinds of matrices. So what are these kinds of matrices? There are p's on the diagonal and 1s on the diagonal. These are the only numbers that can appear, either p or 1. And at any entry such that on the left has a P, and on the bottom has a 1, you can write any number between the 0 and P minus 1. So here I have P1, P1, 1. So you can see that here there's a 1 in the second column. So the 2, 3 entry of the matrix must be a 0, because on the left side of this entry, there's a 1. And for an entry of this kind of matrix to be non-zero, it must have a P on the left and a 1 on the bottom. So you can check that all the zeros are cases where there is no P on the left, or there is no 1 on the bottom. And on the other one around, all the asterisks are just cases where there is a P on the left and a 1 on the bottom. And then I claim that A and A times N, when this is N, are adjacent to one another. Great. So I just stated that either B is A times N, or A is B times N. So both cases will have adjacency. Cool. This wasn't so important. Like you can just, it was just a rule, an algebraic rule to how to connect things. Now, I want you to believe me with no proof or explanation that you can define everything that I defined here using a quotient of the group of invertible matrices over the p-adic field. When you take the projective group of matrices, so you divide by the center of QP, and you take the inside this group. Okay, so there is here the PGL DQP. Inside this group, there lives PGL DZP, where ZP are the p-adic integers, not the p-adic field. And you can quotient the matrices with entries from QP, the invertible matrices with entries from QP by the invertible matrices with entries from ZP, and you will get again the same set of representatives that I gave you before. So you can again think of this coset space as the vertices of the building. But now, if you think of this set in this way, there is a clear left action of PGL DQP on this space. And this is very important. So this space has a left action of PGL DQP on it. And actually, okay, so clearly on its vertices. So it's not so clear why it has an action on the building, but on the vertices of the building, it's clear. And what's quite amazing about it is that this action is so nice. It has many nice properties. One of them is that it is simplicial. It acts simplicially, so it sends actually simplices to simplices, and it acts as an invertible combinatorial map on the simplicial complex. So it sends vertices to vertices, edges to edges, triangles to triangles, and so on. So nice. We have a simplicial complex, an infinite simplicial complex with an action of PGL DQP on it. And I want to do a small interlude. Okay, so it's a very famous thing in the algebraic topology that there is a connection between the fundamental group of a topological space and its universal cover. So given a topological space, for example, the circle, you can look at all paths with fixed endpoints up to homotopy. This will create the universal cover. And the fundamental group of the topological space will act by something called deck transformations on the universal cover. So I'll again go to my iPad for a moment. Hopefully I'll do it very quickly. Right. Okay, so for example, here the fundamental group of the circle is just Z, and the way that Z acts on this universal cover is by, actually the name deck transformation is very intuitive here, because +1 just sends everything one floor upstairs. So everything is sent, every point is sent to the point one above it. +2 is, okay, so maybe let's do +2 in a different color. So +2 is like this map that sends every point 2 steps up. -1 is the one that sends every point 1 step down, and so on. So when you have a topological space, and you look at its fundamental group, it acts naturally by deck transformations on the universal cover. And the more interesting case is not a circle, it's the rows with 2 petals. So every 4 regular graph actually has the tree, the 4 regular tree as a universal cover, specifically the rows with 2 petals. So I'm talking about this thing. And you can look at various other covering spaces of the rows with 2 petals, and all of them correspond to subgroups of the fundamental group of this rows with 2 petals, which is just a free group on 2 generators. And the way you can see the relationship between the subgroup and the group itself is by looking at what are the orbits of the subgroup acting on the universal cover. So the subgroup that is related to this, like the fundamental group of this topological space, is actually a subgroup of the, is a subgroup of the fundamental group of this space, the second one, the lower one. And the way you see the connection between them is by their action on the tree upstairs, by deck transformations. So hopefully I didn't tell you anything new, because these are quite basic in algebraic topology. And I will need at least the main idea here. So let's go back to the slides. So this is the notion of covering spaces, but we should think of it the other way around. What do I mean? You have an action on a topological space. You can quotient up by the action. Look at the orbits of the points, orbits of the edges. If it's a simplicial complex, you can look at the orbits of the cells. And if the action is nice enough such that cells go to cells and so on. And you can look at the quotient space. So this is what I want to talk about. So this is just reversing the idea of what we talked about in the last slide. Instead of taking a space, looking at its universal cover and having an action on the universal cover, we can take an action on the universal cover and translate it to something small, which is the quotient by this action. So you have a group, you have a topological space. The group acts nicely on this topological space, and you can define the quotient space, which is, as I said, just the orbits under this action. Like the points will be just the orbits under this action. And quite amazingly, if the action is nice enough and X is a simplicial complex, you will get a simplicial complex. And if the number of orbits is finite, so every point has a finite orbit, it automatically means that you will get a finite simplicial complex, which is a very nice thing. So this is a finite combinatorial structure that we can actually check things about. Okay, so I gave here an example. Every 2D regular graph is a quotient of the 2D regular tree. And you can check that the way you can get this quotient is by a subgroup of the free group of rank D. So you can, there is a way of defining every every regular graph with even degree using this idea of quotients of the to the regular tree by the action of the free group on it, actually of subgroups of the free group on it. Okay, any questions about that? No? If you feel that you are with me, please write a yes in the participants, because I want to understand how many of you are with me. Ah, great. So most of you are with me. This is nice. Those that are not, please feel free to ask questions, okay? Like this is the point of this talk, for you to understand. Thanks. Someone is away. Okay, so we stated that there is an action of PGL DQP, some group of matrices, on our building, on our nice simplicial complex, and we can ask what is the quotient of this space with respect to a stabilizer of a point. So if you have a group action, it may stabilize some of the cells. So there are elements of the group that keep some cells in place. For example, the identity element stabilizes everything. But there are maybe elements that are not the identity that stabilize some points or edges or something. So in the example that we gave just before, the free group acting on the tree doesn't have any stabilizers that are trivial. Okay, so think about it. The free group acts in a because this is its Cayley graph, so it acts faithfully on it, and it has no stabilizers and nothing. Not just faithfully, freely. This is the correct word. Okay, so now we can ask ourselves, if we take the building, okay, so behind me, there's the two-dimensional building. If we take that building and we take the group and we act with PGL DQP and we ask, what are the elements of PGL DQP that stabilizes a specific triangle? So I take a specific triangle in the picture behind me, and I ask what happens when I take the quotient space of the building with respect to the action of the stabilizer. What I will get is what is called the apartment, an apartment. So there are many apartments. They are all homeomorphic to each other, isomorphic as simplicial complexes to each other, and so on. And if I do the same process, but with a single vertex, I will get what is called the folded apartment. So this is what happens if you take the, okay, so let me go to my iPad again. Right? So this is what happens when you do it for a triangle. So you fix the triangle, say this triangle was fixed, okay? And now, quite amazingly, all other triangles just collapse on it. Okay, so all the triangles that are connected to this triangle through this edge, okay, maybe I'll use another, through this edge, all are mapped to this triangle. Okay, so it is transitive on the triangles that are connected to this triangle via this edge. And in the same way, the action of the group is transitive on all the triangles that are connected to this triangle on this edge, on the blue edge, and similarly here on the green edge. And actually, if you keep on with this idea, you'll get a tessellation of the plane. So this is just a tessellation of the Euclidean plane. And you can check that so for example, if this is the vertex 1, 0, 1, 1, 1, okay, all zeros, this is the 1, 1, okay, 2, 1, 1, This will be 2, 1, 1, this vertex, and this will be 2, 2, 1. So we said that all of these vertices, so say we took this triangle and we modded out by the action of the group on this, by the stabilizer of this triangle in the action of the group, you will see that for any point here, there is a representative which is just diagonal. Okay, so here there is 4 to 1, and I'm not sure what will be the others. This is 2 to 1. This will be 1 to 1, this vertex, and this vertex will be 2, 1, 2. This vertex will be, one of them will be 1, 1, 2. Okay, this will be 1, 2, 2, right? And this will be 1, 1, 2. Okay, and you actually what you get is a copy. This quite amazingly, this quotient is isomorphic as a simplicial complex to a subcomplex of the original complex. So this thing is both a quotient of the building and something that you can represent as something which is like a tessellation of the plane that lives inside the building. So I just gave you the names of the vertices. So clearly here, if you think of it as a quotient, there isn't a single vertex here. There are many vertices that are in the fiber of this quotient. Okay? At this point, at the 4 to 1 point. But I can represent this whole fiber using one of these points, and I can check that there is only one diagonal representative above each of the fibers, in each of the fibers. Great, so this is one. And I want to use the same thing, so I'll just remove everything. And I'll say that you can look at just the stabilizer of 1, 1, 0, and then you will not get this whole tessellation. You'll get some smaller thing. You'll get only this sector of the tessellation. So if you take the stabilizer of the vertex, it's a larger thing, right? So a vertex, all things that stabilize the triangle will stabilize the vertex, but not everything that stabilizes the vertex stabilizes also the triangle. And if you mod out by the things that stabilize the vertex, you'll get actually this sector. And I started with the more difficult example, but I want just now to do the tree. So say you have the 4 regular tree. You can look at it in this way. And then if you look at the stabilizer of this edge, the quotient space of this, the stabilizer of this edge will be just this edge, and then another edge, and then another edge, and another edge to this part, and another edge to this part. And let's give them names. So this will be 0, this will be 1, -1, 2, -2, and so on. And it's easily checked that all of these will be 1s, all of these will be 2s, all of these will be -1s, all of these will be -2s. So the apartment of the one-dimensional building is just the straight line, and you can think of it as the simplicial complex of the integers. Great, but what is the folded apartment? So let's assume this is 1, 0, 0, 1. And I look at the quotient by the stabilizer of this point. You can check that it will do the following. It will just be a ray. So it will fold, this is why it's called the folded apartment. It will fold the left side of this line onto the right side of this line, and you will just get a ray that you can just note the vertices of it by the natural numbers, 4 and so on. Great. So we will probably learn very little about our proof, but I hope that you learned something during this talk. Okay, Costa, maybe tell me what should I do? 5 minutes left, you wrote me. Okay, listen. I will give an overview of what you can do with this idea of the apartment. So I'll go to my slides. Okay, so I wanted to teach you other things, but I want to talk to you, how do you use the apartment to analyze random walks on d-dimensional graphs. So we have here a four regular graph, okay, not dimensional, 4 regular graph. We have the 4 regular tree, and we now saw that we have the folded apartment of this tree as using the Bruhat-Tits building. So I don't think of the vertices of the tree like I used to as elements of the free group. I think of the vertices of the tree as primitive lattices, integral lattices of co-volume a power of 2, a power of 3. If I want it to be 4 regular, it should be a power of 3. And I can fold this tree on this ray, and this will be the fundamental, the folded apartment. And I want to show you what happens when you do a random walk on this kind of thing. Okay, I want to say much. Okay, so I'll give you an example of a random walk. Say you start from this vertex. So I'll give you a probability measure over the vertices. The probability measure of the beginning is just being 100% in this vertex and 0% in every other vertex. So this is my beginning state. After one step, I will be with probability 1/4 here, with probability 1/4 here, with probability 1/4 here, probability 1/4 here, 0 at my beginning and 0 everywhere else. Let's do another iteration for us to feel what happens here. So I'll have 1/8 here, right? I will have 1/16 here. I will have 1/16 here. I will have 1/16 here. I will have, what will happen here? 1/16 here as well. 1/16 here as well. Here I will have 1/8. Here I will have 1/16. Here I will have 0. And I think here I will have 1/16. Here I will have 1/16. And here I will have 1/4 at the beginning point. So you can just check that after 2 iterations of a simple random walk, what is a simple random walk? From each point, you go with uniform distribution to any one of the neighbors of the vertex that you are in. And these are the first 2 iterations. Now, every walk on a 4 regular graph is just the projection of a simple random walk on the tree. So there is a map from here to here, such that at the beginning you were 1 here, 0 everywhere else, like at the beginning there. Then you are 1/4 here, and then 0 everywhere else. Then you are 1/16 at these points. And so on. and 1/4 in the middle, and you can just check what happens next. And again, you can take this walk, the walk on the 4 regular tree, and project it on the folded apartment. Now, the folded apartment here is just a very natural thing in this context, because it just checks what is the distance between the point that you are now to the origin, and it sends all the points of radius 2 to 2, all the points of radius 1 to 1, all points of radius 3 to 3, and so on. So at the first point, we'll get 1, 0, 0, and so on. At the next step, you can check, it will be 0, 1, 0 all along. And the third step will be 1/4 here. 1/4, 3/4, 0, 0, and so on. So I'm just saying there is a connection, a very natural connection between walking on a finite 4 regular graph, walking on the 4 regular tree, and folding this walk on the 4 regular tree back to the folded apartment using the action of PGL2 Q3. I'm finishing, Costa. Yeah, I see. I'll just say the last words. And if you check Peres and Lubetzky's work that I didn't even talk about, and hopefully some of you will be interested and can talk about it with me if they like after the talk. So if you check what they actually did, they took every walk on the finite graphs, they translated it back to the tree, but in the tree, they looked only on fibers of specific elements from the folded apartment. So they looked on fibers from the folded apartments. They concluded something about the fibers of the folded apartment. And from that, they concluded some cutoff results that I didn't even define what cutoff is, but they deduced some cutoff results. And what I wanted to tell you actually, and if it interests someone, again, you are welcome to talk with me after the talk, is how can you translate some of these ideas to the folded apartment of dimension 2, and what are the obstacles, and how Ori and I solve these obstacles, because he had the work with Alex Lubotsky and Eyal Lubetzky before our work, where they weren't successful in generalizing these ideas to the simple random walk, and I think there are interesting things here. So I'll finish here. Hopefully you learned something, and although you didn't learn about cutoff.
So let's thank Michael for the talk first. And are there any questions? So I suggest those who can and have time can stay for another, I don't know, 5-10 minutes. But the official part of the seminar is over. And yeah, I think everyone is, in this setting, everyone is free to leave whenever they want, but we're moving to unofficial part of the seminar now. So
okay, so you want me to stop the video, or?
I think if you can shortly state the main result.
I can state the main result, but the question is how many of the audience know what cutoff is. So maybe let's do small a small survey. So if you want to stay and you know what cutoff is, write yes. If you don't know what cutoff is of random walks on direct graphs, say no. Okay, so we have for people that don't know and want to know. So Costa, I think I'll explain briefly using my slides what is cutoff, like what is the context, what's cutoff, and go back to Peres-Lubetzky, and then you stop me whenever, okay?
Yeah. I think
Peter,
I
it's
personally
okay,
have to. I personally have to leave in 10 minutes, but I think you can go on until there are people interested.
Cool. Okay. Thanks. So we'll do a stop in 10 minutes anyway and say,
Okay.
understand where we are. So I will go back to some ideas. Okay. So we just said what an apartment is, and I said that you can just say, you can choose vertices of the original building and the simplicial complex generated by these vertices, and the vertices that you need to take for the apartment is the upper one, and for the folded apartment is the lower one. So this is just an algebraic view. And now I will talk briefly about what is cutoff and what is like about random walks and so on. Okay, so if you have a deregular directed graph, D, you can define a random walk operator on it in the following way. If you have a probability measure on your graph, you can define the probability measure after one step. So P acts from the right on the probability measure. And at every point, so this is a graph, so the probability measure gives any point a number. So the new number at a point is just the average of the numbers that were written on the vertices that have an edge into this vertex. Okay, so for any vertex X, the new number is the average of the sum, it's like 1 over D times the sum of all the numbers that were written in vertices that have an edge into this vertex. Okay, so I'm just stating that this is also, like, the way I define it is as an operator on L1 of D, but actually it's also a bounded operator on L2 of D, so we can use it, it's a bounded operator on a Hilbert space, and there's a spectral analysis of these kinds of things, and this is a nice operator. And two examples of this kind of thing is the simple random walk and the non-backtracking random walk. So I'll just show you what does it mean. So you can look at any graph that is not directed and replace any edge. Here on the right, you can see that any edge becomes two edges, one edge to the right and one edge to the left. So any non-directed edge becomes two directed edges, one at each direction. And then if you do the random walk that we talked about a moment before, you will see that at any point it will just average what happens on all your neighbors. So the probability at any point is just the average of what were the probabilities at any of the neighbors at the previous point, time point. And the non-backtracking random walk, okay, so this was an operator on vertices. You can now define an operator on directed edges. So if you do the same thing and you replace the edges by vertices, and you say that an edge is connected to another edge if it is actually on the right path, right? Like if you have an edge from X to Y and then edge from Y to Z, and Z is not X, you are allowed to move from XY to YZ. So this is the interpretation of the drawings downstairs. This is called the non-backtracking random walk. So again, I'll just state, the simple random walk is a walk on vertices. The non-backtracking random walk is a walk on edges, on directed edges of the graph. So in the procedure that we talked about before, you take a graph, you replace its edges by directed edges. The directed edges become vertices, and there is a rule of when a vertex is connected in a directed way to another vertex. Cool. So these are pictures by Parzanchevski. I try to write on all the pictures where they came from. So either from Google or from actual talks. So, I explained briefly what is the simple random walk and the non-backtracking random walk. So I think I will not tell you more about that. Now I'll tell you some conditions on when does this walk has a stationary distribution, has like a limit point. Okay, so if D is deregular and it's finite, so the number of vertices is finite, you can show that the operator, that the random walk operator on the directed graph tends to the uniform distribution on the vertices. Okay, so if you do this operation again and again, you tend to the uniform distribution, actually in almost any metric that you can think of. So whether you check it in L1, in total variation, which is almost the same, in L2 and so on, this distribution tends to this distribution. Right, so you think of it as distance between vectors. Sorry. Okay, so the question is how fast is this distribution tending, like how fast does mu p to the t tends to 1 over n? So clearly it depends on the mu, right? So if you start with 1 over n, you can check that you stay in 1 over n no matter what you do. So if you should ask something like, what is the worst mu such that it will take the longest to get the closest to 1 over n. And for this analogy to work, you need to define what is called the mixing time. So for any number, so if you want to be 0.1 close, so epsilon will be 0.1, for example. If you want to be 0.1 close in total variation to the uniform distribution, the mixing time is the first occurrence, like the first power of the matrix, the smallest power of the matrix, such that no matter what the probability distribution was at the beginning, here I just took the Dirac measures, but it's enough to take the Dirac measures. No matter what the probability measure was in the beginning, if you do this process t times, and then you take out pi, here is 1 over n, it's the uniform distribution, and you check what is the one norm of this distribution, it is smaller or equal to 2 epsilon. The 2 here is just some normalization because I took the one norm. So this is the mixing time of the operator, of the adjacency operator, the random walk operator on the directed graph. And you can think of it as something that starts very large, very close to 1. And you know that at infinity it tends to 0. So the question is, what is the behavior of this function? Like t mix epsilon, when epsilon tends to 0, what happens to t? Okay? And you believe that as if you want to be as close, very, very close to the uniform distribution, you need to wait a very long time. Okay, this is like the idea. But there is a notion of cutoff, and it is the following. If you take a sequence of graphs, of directed graphs, all with the same regularity, I said that it exhibits cutoff if no matter what epsilon is, the epsilon mixing time and the 1 minus epsilon mixing time are about the same when the graph tends to infinity, when the graphs get larger and larger. Okay, maybe I should stop here for a moment just for you to ask questions about this notion, because the way I think of it is as follows, okay? I'll give you the idea. Say you are in a poker tournament, okay? And you want the deck to be quite shuffled. And maybe you are an amateur player. So the poker tournament is an amateur poker players tournament. you will want the deck to be maybe less, you don't expect the deck to be shuffled as much as in a professional poker tournament, right? Like in a professional poker tournament, probably there are very strict rules on how many shuffles of the deck you need to do for the play to be okay. Like, I don't know how to say it. But what does cutoff mean? It means that if the deck gets larger and larger, if you believe that shuffling cards has the cutoff phenomenon, and it has the cutoff phenomenon, if the deck tends to infinity by size, it starts to know, it doesn't matter whether you want to be 0.9 away from the stationary distribution, which is all the permutations on the cards, or 0.1 away from the stationary distribution. So it doesn't matter what your standards about the distribution of cards is, because it will take about the same time to mix it professionally as it will take if you want to mix it amateurly. So this is a way of thinking of the cutoff phenomenon. Okay, so you can think of a directed graph that is related to this process of processing. Ken Costa.
Yeah, so I have to go, unfortunately. So I will say thanks for the talk and remind to others that next week Zhenya Sapir is going to give a talk. And thanks everyone. I'm out.
Thanks, Costa. So I'll finish in like 10 minutes at most. So I'm sorry that I'm keeping you here. People went out already, so feel free to go as well. So as I said, this is a way of thinking of what is the cutoff phenomenon. It doesn't care, this process doesn't care about your standards. The moment that you are a bit smaller than 1, you will be very smaller than 1 and very close to 0. Okay, in a very short period of time. Okay, so these are some pictures of this thing. So you can see that at the beginning, you are very far from the stationary distribution. And then at some time point, in a very small window of time, you get very close to 0. So these are like the most natural pictures of the cutoff phenomenon. And I wanted to state that we showed the simple random walk and the non-backtracking random walk, but there can be defined walks on simplicial complexes that are a bit more interesting. So you can define a walk on triangles, for example. So you start from one triangle, which is ordered. So I order the vertices of the triangle, and I move to another triangle with the following order. So I start from X, Y, Z, and then I will go to Y, Z, W, such that W is not the original X. And this will move me to a new triangle, right? So I will not be in the triangle that I started with, and I will keep thinking of my triangles as ordered. And if I'll keep this process, I will move along in the building. You can check that if you start from a blue, red, green triangle here. So if, for example, you start from the red, blue, green, you will move to a blue, green, red triangle. So the colors will just permute in a cyclic way. And you will move on, and you will see that you will move out of, like you will get far and further and further away from your starting position if you do this kind of a walk. So it's very similar to the non-backtracking random walk on the tree. So if you do a non-backtracking random walk on a tree, you'll get further and further from the origin point, and you will never go back. You will never non-backtracking. And if you do this kind of walk on the building, again, you will just drift away in one direction in the building, and you will never get back to a simple, to a cell that you've been in already. Okay, cool. So these are interesting walks on the building. And I'll just tell what a Ramanujan complex and graph are. So the results that I'm talking about, that I will talk about, are results about Ramanujan graphs and Ramanujan complexes. So you should think of a Ramanujan complex, where a graph is just a specific example, as a quotient of the building that mimics the building spectrally. So the eigenvalues of operators of interesting operators on this finite simplicial complex behave in the same way as on the building. So in the graph case, it reduces to the following condition. I said that a deregular graph is Ramanujan if the non-trivial spectrum of the simple random walk, so the only operator that I care about is the simple random walk, you can check what is the spectrum of this operator on the finite graph. You can check what is the spectrum of this operator on the tree, on the deregular tree. And if the non-trivial, so the things that are not D or minus T, are contained in the universal cover, in the spectrum of the tree, we call it Ramanujan. So this just means, okay, I'll go back just a moment. So this just means, in other ways, just that the spectrum is 2 squared D minus 1 is between the absolute value of the spectrum. Whoa, it's hard to write with this. Is smaller or equal to 2D, 2 squared D minus 1, or plus minus D. So I allow you to have these two eigenvalues of the simple random walk, but I don't allow you to have any eigenvalues that are outside plus minus 2 square root of D minus 1. This is what happens in the tree case. Okay. Oren says that he needs to go as well. Okay, so I'll again just say that a Ramanujan complex is something the same, but I ask that all operators on cells behave nicely. So it's a stronger condition in some sense than being a Ramanujan graph. In the graph case, they are the same, but in the general case, they are maybe different. And I think I'll finish here. Like maybe we are very few that are left. Maybe just ask questions if something interests you, and say that it doesn't interest you if it doesn't. Okay, I'm finishing here. I'll stop the share and stop the